Swayam Prabha. Digital India. Educated India.
All right, so let's continue our discussion related to digital circuits. So in the last lecture, we had seen the advantages of taking in an analog signal and converting it into a digital number. And so let's continue with the discussion here. And let's look at the numbers because the numbers can be represented in different base. We are all familiar with the decimal number system. With digits where we express a number in terms of digits 0 to 9. And we, of course, use a positional representation. And you also must be familiar with the binary system. So let's continue that discussion here. So every number system is associated with a base or radix. And obviously, a positional notation system is something that is very convenient to represent numbers. And so if we have a number, A5, so these are the different positional digits that are there, A0 to A5. And if the base is R here, then the value of that particular number is, because the first digit carries a weight of R to the power 0 here, the second one carries R to the power 1, and so on and so forth, R to the power 5 here. And we're all familiar with the decimal system where R is 10. Right, and we use the symbols, the possible values that A0, A1, A2, A5 can take are from 0 to 9 here. So that's a decimal system with a base 10. And similarly, for example, so we know how to, when we write a number like this to the base 10, then we are familiar with it. This is what the value of that particular number is. We can expand it in this particular manner here. And also, if we have a decimal point here, then the first digit after decimal is 10 power minus 1. The second one is 10 power minus 2. All right. Well, so that's a decimal system that we are familiar with. Now, we could take the base or the radix R as 8. So that would become an octal number system. And that would use the symbols 0 to 7 here. And so, for example, if there is a number 2007 to the base 8, well, the value of that particular number would be 7. The weight of that particular is 8 to the power 0 here. The second one is 00, so 8 to the power 1 and 8 to the power 2. And then 2 is 8 to the power 3 here. Right, so what decimal number does it represent? Well, you multiply them all together. And that's equal to, so 2007 to the base 8 is equal to 1033 to the base 10. Well, this is a hexadecimal system is something that we use commonly in digital circuits. So that's a system with a base of 16. And you'll see why in later part of today's lecture here. So hexadecimal system uses the symbols. So it has a base 16, so it will use 15 distinct symbols. Or 16 symbols, including 0 here. So 0, 1, 2, 3, 4, 5, 9 up to 9. Then 10 is represented as A, 11 is B, 12 is C, 13 is D, 14 E, and 15 F. Right, so 0 to F here. So these are the symbols that we will use to represent the different digits that are there here. So for example, a number 2, B, C, 9 to the base 16. So that corrected, this is to the base 16. So its value would be, the first one would be 9 into 16 to the power 0. The second one, C, is 16 to the power 1. The third one is B, 16 to the power 2. And 2 is here, 16 to the power 3 here. And converting it into a decimal number, again, this is 16. So converting into a decimal number, so convert C. C is actually 12. If you go and see, C is 12. And B is 11. So convert that back into here. And so when you write a number like this, 2BC9 to the base 16, so that is equivalent to 11209 to the base 10. Right. Now, the most important number system for our interest is the binary system. So that has a base 2 and uses only two symbols, 0 and 1, to represent all the numbers here. So note that each one of those number system can represent any number. And so preference for one system over the other depends on which number system is easier to use. And for us humans, when we are doing the computation, for us the decimal system is the most convenient one. When we build circuits, the binary system turns out to be the most convenient system for doing any computation. So when you write 1101 to the base 2, now each position has a different weight. So the first one, the lowest significant bit here, 2 to the power 0, then 2 to the power 1, 2 to the power 2, and 2 to the power 3 here. So we can write it in this form here. And it's easy to convert it into the decimal system. So you convert 2 to the power 3 as a decimal digit 8 and 4 and so on and so forth. So this is equivalent to 13. Right? And what about when you have a decimal point here? So this carries 2 to the power 3. This has a weight of 2 to the power 2 and so on and so forth. This one carries a weight of 2 to the power -1, half, 0.5. This one is 1 by 4, 0.25, and 1 by 8, and then 1 by 16. So that's the different positions, the weights associated with different positions here. All right, so, so 2 to the power 3 is 8, 2 to the power 4, 16 is here. 2 to the power 10 is, sometimes we use the word, if you have 2 to the power 10 bits here, so we'll say 1 kilobit here. But note that kilo is not exactly 1000, it is 1024. And 2 to the power 20 is 1 mega, but 1 mega is not exactly 10 to the power 6. Note the difference that is there here. And 2 to the power -1, of course, these are we are familiar with. Okay, so since in digital circuits we deal primarily with the binary numbers, so one needs to develop a fluency with binary numbers, in the sense that when a binary number is given, we should be able to quickly calculate or assess what that particular number represents in decimal notation, because that's the notation that we are familiar with. So 11001 is so the first one is 1, and this one carries a weight of 8, and this one carries a weight of 16. So 16 and 8, 24, 24 plus 1, 25 here. And similarly, we can, so practice and see that this one, so is 64 plus 32 plus 1 is 97 here, 0.101. So this one weight is 0.5. This is 0.25 and this is 0.125 here. So 0.5 plus 0.125 is 0.625 here. 11.001. So I shouldn't say 11.001. So 11 is 3 and 001. So 0.5, 0.25. This is 0.125 here. So it's 3.125 here. All right. So converting a binary number into decimal is straightforward. All you need to do is use the proper weights for each one of those positions and add them up, and you get the number in the decimal one. How do we convert a decimal to binary number? So for example, if you have to convert 45 in decimal notation to binary number here, so 45 to the base 10, and the binary number, let's say, consists of n digits. We don't know how many digits are there, so let's say n digits. So bn -1 up to b0 here. So B0 is what we call is the least significant bit, and the last one is what we call is the most significant bit here. So if this is the binary number, so this binary number, we can convert it into a decimal number by using this transformation here, B0 plus B1 2 to the power 1 and so on and so forth, Bn 2 to the power n here. So this is equal to 45. And we have to find out these values here, B0, B1. So each one of them can be either 0 or 1. So suppose we divide both sides by 2. So we divide left hand side by 2 and we divide right hand side by 2 here. So 45 by 2, so we know is 22.5 here. And we divide by 2, so 2 to the power n becomes 2 to the power n -1. The last one, B1, 2 to the power n becomes 2 to the power 0. And this one becomes B0 into 0.5 here. So if we compare the left and the right hand side, we note that this part from B1 to Bn here, it has to be an integer here, so whole number. And therefore, so B0, then if you want to match the left hand and the right hand side, B0 has to be equal to 1 here. If B0 is 0, then there's no way that you'll be able to get a 0.5 on the right hand side here. So B0 is 1. So we figured out that B0 has to be 1. So once we figured out B0 has to be 1 here, so B0 is 1, then what we can do is, well, we can take B0 1, so we can take B0 out here and then focus on 22. So we know that 22 must be equal to the rest of the number here. So let's focus on this here. So now it's a iterative method here. So the procedure that we use for finding B0, we can use it to find B1 also. So let's divide by 2. So we divide both sides by 2 here. So we get 11. But if we get B1 into 0.5 here, no, there is no decimal 0.5 here. So this B1 has to be 0 here. So this B1 is 0 here. And so let's take that out. B1 is 0. So this number now then must be equal to 11. So let's divide it by 2, 5.5. And so that tells us B2 equal to 1. And we repeat this process and till the left hand side becomes 0 here. Left hand side is exhausted. All right, so 2.5. B3 is 1, 2, 1 here. B4 is 0. And we compare the two, then B5 has to be 1. So till the left hand side becomes 1. Then the whole procedure ends, and we see that we need total number of 6 bits from 0 to B5, B0 to B5 here. And so this is the number here, 101101. So this binary number is equivalent to 45 to the base 10 here. So we see that we can convert a decimal number to a binary number by repeatedly dividing this particular number by the base of this particular number here, which is 2 here. All right, so we can do it. So it's a method of successive division by 2 here. So we can do it in a more systematic manner here. So 45, so we divide it by 2, we get 22, and we get a remainder 1. Then we divide this side here, 11, we get a remainder 0. We divide it again, 5, we get a remainder 1. We divide it here, so by 2 again, so we get 2 here and we get 1 here. We divide by 2 here, 1 here, and 0 here. And so a number, and then we take 1 over here and here. So our number becomes 45 becomes 101101. So all the remainder part is what the binary number is. And this is the most significant bit, and this is the least significant bit. So it's basically the same algorithm that we just saw earlier by repeatedly dividing by 2. And through that we were able to figure out what is B0, B1, B2, B3. So this is a more compact, more systematic, one may call, representation for doing the same thing here. And so we can convert any number, any decimal number, into a binary number by following this particular procedure here. Now we can use this particular process, so the process can be generalized. We are converting into a binary number. Well, if for some reason, let's say you're interested in converting a decimal 153 to an octal number system, well, you follow the same procedure here, 153 to the base 10, then is equal to B0 plus B1 8 to the power 1 here, and similarly, then you divide both sides by 8 here. So you get 19.125 here, and so therefore B0 by 8 must be equal to 0.125 here. Again, same thing after decimal. This part cannot contribute to this after decimal point, so B0 by 8 must be equal to 0.125, so B0 is equal to 1 here. And so same thing, 153 here. So instead of a more compact way of doing the same thing, we divide by 8. So we divide by 8 and we look at remainder, we divide by 2, look at remainder, and like that. So in the end, the 2 is carried over here and we get 0 here. So the number then becomes 231 to the base 8 here. All right, so converting decimal to binary number, let's say when we have a decimal point here, 0.35 to the base 10 to a binary number here. So note that in this case, it is 0. All this here, b minus 1, b minus 2, these are the bits here. And in this case, instead of dividing by 2, it will not help. Multiplying by 2 will help you. So let's write it down. 0.35 is equal to 0 plus b minus 1, 2 minus 1 here, 2 to the power 1 by 4, and so on and so forth. So let's multiply by 2. Okay, so multiply both sides by 2 here. So we get 0.7. And so 0 is out. So we get here b minus 1 plus so on and so forth. And note that there's nothing before the decimals. This is 0 here, so b minus 1 has to be 0 here if you match the left and the right hand side. So 0.7 must be equal to the rest of the number here. We multiply by 2 again. Now we get 1.4, and comparing the two, we know that b minus 2 must be equal to 1 here, because the rest of the number, note that the rest of the number cannot be equal to 1. It will always be less than or equal to 1 here, right? So b minus 2, to match the left and the right hand side, b minus 2 must be equal to 1 here. All right, so once you do that, then you take b minus 2 out, you take 1 out, so you're left with 0.4. It must be equal to the rest of the numbers here. So you get this here, and then keep on doing the same thing here. So you multiply by 2.8, so b minus 3 must be equal to 0 here. Right, so a more systematic way of doing the same thing. So start with 0.125, multiply by 2, you get 0.25 here, so you get 0 here. Multiply by 2, you get 5 here, you again get 0 here. Multiply by 2, you get 0 here, and you get 1 here, right? So what is the number? The number is 0, 0, 1, right? So 0, 0, 1 here. This is the first bit here, and this is the last bit here, 1 here. Okay, what about 0.8125? Let's do this again here. So 0.8125 here. So after the dot here is 8125, let's multiply by 2. So we get 1.625, that's multiply by 2, this part only. We get 1.25 here, let's multiply by 2 here. We get 5 here, let's multiply by 2 here. We get 0 here, and we get 1 here. And the number ends here. So what will be our binary representation? Well, it will be 1101. 1101. Note again, the 1 here is represented by this bit here, and the 1 here is represented by here. So you go down and write down the number 1101 here. Okay, so we've been saying it that each binary digit is what we call as a bit here. Okay, and so this is if we count, this is a 10-bit number here, and this is what we call as the least significant bit here, LSBs, and this is the most significant bit here, which we call as the MSB here. And so depending on the kind of number that you want to represent, you may need 2 bits or 3 bits or 4 bits or more. 2-bit can only represent 0001, 1011 can only represent from 0 to 3. 3-bit can represent from 0 to 7. 4-bit can represent from 0 to 15. And 5-bit can represent 5 and 6 and so on and so forth, can represent a larger number. So depending on the kind of number that you're handling, you may require that number to be represented by 4 or 5 or 8-bit or 16 bits here. So an n-bit binary number can represent numbers from 0 to 2 to the power n minus 1 here. So 3-bit 2 to the power 3 minus 1 is 7, so it can represent from 0 to 7 here. So converting binary to hex and hex to binary here. All right. So note that even for a number like let's say 15, we need to represent it by a fairly large number of bits, 0, 1, 1, 1, 1, 1 here. So imagine if you have to represent, let's say 950. So you'll require lots of bits to represent. And so writing that large binary number can become cumbersome. And therefore, there's a compact representation, which is the hex representation. And hex and binary are directly related to each other. It's very easy to convert them back and forth here. So hexadecimal is, these are the symbols. 0, we've already seen 0 to F. F representing 15, C is represented by 12, and 0 till 9 is the same thing here. So A is 10 here. So suppose there's a binary number and we want to convert it into hex. So Well, this binary number then is equal to B0, B1 2 to the power 1, and so on and so forth, 2 to the power 7 here. So it's an 8-bit binary number. And we'll see that you need only 2 hexadecimal digits to represent it. So this is equal to H0 plus H1 16 to the power 1 here. Now what we can do is we can group the first 4 bits together here. So group the first 4 bits like this here, and the next 4 bits like this here, and take out 2 to the power 4 here as common between these 4 here. So this you obtain this part here, and you obtain this part here. So this is what is equivalent to H0 here. If you match now the left hand side and the right hand side here, so note that this is 2 to the power 4 is nothing but 16. So this is what represents H0, the hexadecimal digit here, and this is what represents the hexadecimal digit H1. Okay, and so it's very easy to convert it. All you need to do is just take 4 of these bits together and group them. So when you have this, so 0011 is nothing but 3, so that's equal to 3 here. 1011, so it is 8 plus 3, 11, and 11 is, note that 11 is represented as B, right? So we will write it as B3. So this big binary number, 8-bit binary number, can be represented as only B3 in hexadecimal format here. And so, you know, instead of writing this 8-bit number like this here, we can write it like B3 hex here. It's understood whenever you use A, B, C, D and all that, it's understood that B3 and this is H here. And converting it back, okay, so once more, what about this binary number? How do we convert it into hex? So starting from the least significant bit, take the first 4. So group them, 0011, and the next one is 11. So this is represented as 33 hex here, right? And what about converting a hex number back to a binary number? Well, for example, E is represented as, go back here, E is nothing but 1110. So you write it as 1110 here. And C is here, C is 12, 1100 here. And then, so you write each one of them as a 4 bits to represent E, 4 binary numbers to represent E, and 4 binary bits to represent C. And then remove the bracket, and then that becomes the binary number here. So note that is the conversion of binary number into hex and hex to binary is just straightforward. And therefore, many times when we have big binary numbers, we don't write them as binary numbers, we write them as hex numbers. And because it's a much more compact representation. All right, so that's as far as the different numbers in different base or radix is concerned. And so for us, the most common, or for this particular course, the number system that is important for us is the binary, and hex as a compact way of representing the binary. We are not going to do computation in the hexadecimal system. Our circuits will not work in hexadecimal system. So hex is only being used as a compact way of representing the binary numbers here. All right, so binary addition and subtraction. So when you have a number, it's not enough to just represent something as a number, but you want to do computation on it. And computation would involve addition and subtraction and multiplication and divisions, right? So how do we add up 2 binary bits? So 0 and 0 is 0. 1 and 0 if you add up is 1. 0 and 1 if you add up, obviously 1. And 1 and 1 if you add up, 1 and 1 is 2. And 2 in binary is represented. So when you add up 1 and 1, you get 0, and you get a carry, which is 1 here. And if you add 3 ones here, 1, 1, 1 here, so you get 3. So it's 3 of them, so you get 1 here, and there's a carry, which is 1 here. All right, so that's the simple addition of bits that is there here. So that's addition of 2 bits or 3 bits that is there here. 3 bits we require because we will, when we have carry, then we will have to add 3 bits together here. Okay, and so how do we add up? Let's say, so recognize that this is 5 and this is 6 here. So let's add up in a positional representation number system. So 1 plus 0 is 1 here, 1 and 0 is 1 here, and 1, 1 is 0 and 1 here. So we use this here. 1, 1 is 0 and 1 here, right? So 1, 0, 1, 1. And make sure that this is 7 plus 6 is 13, and so this is 8, and this is this number is 2, base 2 plus 1 here, so that's 13. So let's do this here. 1 plus 0 is 1, 0 plus 1 is 1 here, 1 1 is 0, and carry 1 here, and 1 1 1 will give us 1 and with a carry here, right? So that's how we add up numbers. That's how we do binary addition. All right, now subtraction, we look at subtraction in slightly different way. We can of course subtract in this particular manner also, just like we are doing addition, but we'll look at subtraction in slightly different way here. And for that, we want to introduce the concept of a complement of a number. So in decimal system, we can use the concept of what is called 9's complement and 10's complement. Okay, so what do we mean by that? 9's complement of an n-digit number x is 10 to the power n minus 1 minus x here. Okay, so let's say there are there's a 2-digit number, and 10 to the power n is 100 minus 1, so it's 99 minus x here. All right, so x is, let's say, 30, so 99 minus 30 will give us the complement part here. All right, so whatever remains from the maximum 2-digit number, which is 99 here, is what is called the complement part. And 10's complement of an n-digit number x is 10 to the power n minus 1x. So basically 9's complement of that particular number plus 1 here. Okay, so for example, you'll see why we are doing this. And 9's complement of 85. So it's a 2-digit number. So what we do is 2-digit number means 10 to the power 2 minus 1. So that's 99 minus 85. So it's 14. So complement means this number is 85. And so whatever remains till 99 is what is the complement part here. Okay, so 85 here. So it's complementary to, so if you have a number line from 0 to 99 and you divide it into 2 parts, so up to 85 is what represents your number, and the next part, the complementary part, is what represents the remaining part here, which is 14 here. So 9's complement of 1, 2, 3, there are 3 digits, so we subtract from 999 here. So that's 876 here. 10's complement of 1, 2, 3 is 9's complement of 1, 2, 3 plus 1 here. All right, so that's the 10's complement here. So 876 plus 1, so 877 here. All right, so you've done a lot of computation in decimal system, and you've never done a 9's complement and 10's complement, and that's because these are not really necessary for us to do computation in the decimal system. But these are convenient when we go to binary. All right, so for example, if you take a binary system, then you can talk about 1's complement and 2's complement. All right, so 1's complement of an n-bit number x is 2 to the power n minus 1 minus x here. Okay, so 2's complement of n-bit number is 2 to the power n minus 1 x here. Okay, so similar thing here. For example, what is 1's complement of 1011? Well, how many bits are there? 4 bits. 4 bits are there. So 2 to the power 4 minus 1 minus 1011. So note that 2 to the power 4 minus 1, so 2 to the power 4 is basically minus 1 is 1111 here. Okay, and so you have to subtract 1011 from here. So 1111 minus 1011, and then it's easy to see what the answer is. Okay, 0100. And the point is that when you're taking 1's complement of 1011 or any number, 1's complement can be obtained very easily of any particular binary number by simply flipping the bits, because you see you're subtracting from a number 1111 here. So you flip this bit here, flip this here, flip this here, it becomes 1, and you flip this here, it becomes 0 here. So 1's complement is simply obtained by flipping a bit here, by changing 1 to 0, 0 to 1. Okay, for example, if you have like this, flip every bit. If it is 1, make it 0. If it is 0, make it 1 here. All right, so it's very easy to compute 1's complement of any binary number here, simply flipping the bits here. And flipping the bits is also very easy in the form of a circuit. Okay, so for example, converting a 0 to 1 or a 1 to 0, you know that it's an inverter circuit. If we think of 0 as a low voltage and 1 as a high voltage, so an inverter circuit is very quickly, it can flip a bit here. 2's complement of 1010 is 1's complement of 1010 plus you add 1 here. All right, so we've already seen what is the ones complement here, and then you add one particular thing here and you get that. Okay, so 2's complement of 110010 here. Well, so you can do that. So you can take a ones complement and then you can add one later on. There's a simpler method of writing 2's complement of any number, and the method is that leave all least significant zero as they are. Leave first one unchanged and then flip all subsequent bits here. So we have a 0 here, leave it as it is. Then we have a 1 here, leave it as it is. And then after that, flip all of them here. Right, so 0, 1, and then you flip 0, it becomes 1, and then you flip here 1, and then 0, 0. So that becomes the 2's complement of this particular number. 1, 0, 1, 1. What will be the 2's complement? Leave the first one. There's no 0 here initially, so leave the first one unchanged. And after that, flip this here, 0, 1, 0 here. You can verify that these are the correct ones here. So what about this one? We leave the initial zeros, all zeros unchanged, 0, 0 is unchanged. The first one that you encounter is also unchanged. After that, flip all of them here. So this becomes 0, this becomes 1, 0, 0, 1, and 0 here. So 2's complement, very simple way one can obtain 2's complement of a number also. All right, so why are we doing all this? 9's complement, 10's complement, and 2's complement and all that. Why are we complicating life? Well, let's illustrate how one could do. So our interest is in subtraction. Our interest is in negative numbers. So positive numbers is fine. We've seen how we can take, add up two positive numbers. But of course, numbers can be positive and negative. And you have to, subtraction can be thought of as addition of one positive and one negative number here. So you want to represent negative numbers also, and you would like to add up positive and negative numbers also. And in that context, this notion of complement can be useful here. So let me illustrate. All of you know, of course, how to do subtraction, but let me illustrate how you can do subtraction in a different way here. Okay. So suppose we're talking about the familiar decimal system, right? So suppose there x1 and x2 are two n-digit numbers here. And you would like to subtract x1 minus x2. That's what you would like to do here, okay? x1 minus x2. So of course, you know how to do it, but so what we are showing you here is that you can do subtraction by actually doing addition, provided you take the tens complement of the number that you are subtracting. Okay, so let's see. So the idea is we are trying to do x1 minus x2. So x2, you take a tens complement and feed it into an adder here. So what you're doing is you're adding up x1 and the tens complement of x2. And of course, when you add up two numbers, you get a sum and you get a carry. And so carry is fed into a NOT gate, which means it inverts it. So you look at, this is called sign. Okay, so when you're subtracting, you can get a positive number or you get a negative number here. So if sign is 0 for positive number and sign is 1 for negative number here. So now the output, the final number, y equal to s if sign equal to 0. So if it's a positive number, then y is simply equal to the s, the sum that you get here. If on the other hand, sign is 1, it indicates a negative number. And to find out the magnitude of the negative number, you take a tens complement of s here. All right, so fine. So let's try and understand that through an example here. So let's say you're trying to do 8 minus 3. 8 minus 3 here, so we take a tens complement of 3. So how do we take a tens complement of 3 here? So we take a nines complement. So we subtract 3 from 9, which is 6, and then we add to it, so it becomes 7 here. Okay, or effectively 10 minus 3, which has become 7 here. So instead of subtracting 3 from 8, and we know the answer is 5, what we are saying is you take a tens complement of 3, which is 7, then you add up these two. So 8 plus 7 here. So when we add up 8 plus 7, so we'll get, because it's a one-digit number here, so we'll get 15. Now 8 plus 7 is 15, so carry is 1 here, and this is 5 here, right? So when you take 1 here, the output here is 0, which means sign equal to 0, it says it's a positive number. And when it's a positive number, our algorithm is telling output is nothing but equal to s here. So output is 5 here. right? So 8 minus 3, we expected 5 and we got 5. But we got 5 through a different route, in the sense that we didn't do subtraction. We didn't directly subtract 3 from 8, but we added two numbers here. One is 8 and the other one is a tens complement of 3, which is 7 here. And we got the right answer that we were looking for, 5 and 0 here. All right, let's do the other thing here. Suppose this was 3 and 7 here, right? So 3 and 7. So we take the tens complement of 7, which will be 10 minus 7, which is basically 3. We add up 3 plus 3. We get 6 here. And we get 0 here. So 0 here, and the output here will be 1. So it means that the number is negative. That's the sign of the number. So when it is 1, it is negative. And 6 here, so it says, well, the 6 number, if you want the magnitude of that negative number, takes the tens complement of this one here. So when you take tens complement of this, so you do 10 minus 6, which is equal to 4. So what it says is 3 minus 7 is, sign is minus 1, minus here, and the magnitude is 4 here. So the number is minus 4 here. Right, so we get a right answer here also. Now, why are we doing all this complicated way of subtraction here? Now, this way of subtraction would make sense if subtracting a number, or basically doing a tens complement, were very easy. If doing a tens complement were very easy, then what we are saying is the following. Subtraction is basically then similar to addition. So in the sense that if you had a circuit which could add up two numbers, then if you took a tens complement of that negative number that is here, and then you add it up, and then you can do the subtraction with that adder also. So you don't have to, which we will see in a minute. So you don't have to build a separate, let's say, system or a circuit for doing subtraction. If you have a circuit for doing addition, well, you can use that particular circuit for carrying out subtraction also, provided that number that you're trying to subtract, if you represent them in tens complement here. So obviously you may be thinking that, well, you're trying to subtract 3 from, or 7 from 3, but then to subtract, you're also subtracting 7 from 10. So what are you gaining? Well, in decimal system, we agree that it doesn't make so much sense. But note that here, you're only subtracting from 10. So you're subtracting any digit from 10. And if that happens to be very easy, then maybe, there's something to be gained by doing subtraction in this particular manner here. So obviously for decimal system, if it made a lot of sense, all of us would be doing tens complement and nines complement for doing subtraction. We don't do that. But for binary system, it makes a lot of sense here. Okay, so let's look at advantage of using twos complement here. So the idea is that, let's say we have made a circuit which can add up two binary numbers, x1 and x2, and it will give us a sum and it will give us a carry. Now we want to carry out subtraction also, x1 minus x2. So the idea is, do I build a separate subtractor circuit? And know that another piece of circuit that you have to build will take up, will add additional cost. And so if you could do it with the same adder, then that would be beneficial. That would be a more efficient way of doing it. So the question that is being posed is, can we do x1 minus x2 using the same adder? Well, similar procedure here. And so we'll go into a little bit more detail here as to why, in the last particular one, you can obviously figure it out very easily by yourself why that particular method of tens complement and was working. But let's look at this particular way of doing subtraction using twos complement in a little bit more detail here, right? So x1 and x2 are 2 n-bit numbers here. And so 2's complement of x2 is nothing but 2 to the power n minus x2 here. So what we are saying is, you want to do x1 minus x2, but you add up x1 and 2's complement of x2 here, right? So you're going to add this up here. So obviously the sum and the carry that you will get here would be the binary representation of x1 plus 2 to the power n minus x2, right? So you're adding up these two numbers here, x1 plus 2 to the power n minus x2 here. Note that the carry will occur only if x1 minus x2 is positive here, because 2 to the power n is n plus 1 bits. Note that the sum is n bits and this is the carry bit here. So each one of these numbers is n bits here. So 2 to the power n is nothing but there is a carry bit already here, 1 here. And if x1 minus x2 is positive, then there will be a 1 here which will then get inverted and will give rise to 0 here. So if x1 minus x2 is positive or x1 is greater than x2, sign will be 0 here. On the other hand, you can also see here if x1 is less than x2, then this whole number will be, there will be no carry here. This whole number would be less than okay, so let's look at it here. So note, carry will only be there if x1 and x2 is positive here. A 0 carry implies a negative number whose magnitude x2 can be minus x1 can be found as follows here. So if there is 0 carry here, which means note that if x1 is not greater than x2, if x1 is less than x2, so the whole number becomes less than 2 to the power n, obviously, and less than 2 to the power n means no carry here, because then it can be represented by only 4 bits here and no carry here, right? So when you don't get any carry, it means here that x1 minus x2 is negative here. So that's what we are saying. If you don't get a carry here, then the carry will be 0, sign will be 1 here. So that means a negative number here. All right, so that part is clear. Why is sign equal to 0 for positive numbers and why is sign equal to 1 for negative numbers here? So a 0 carry implies a negative number whose magnitude x2 minus x1 can be found as follows. So we have said once it is a negative number, and if you want to find out what is the magnitude, takes the 2's complement of that particular number here, whatever number you get here. So s is, note that s is nothing but x1 plus 2 to the power n minus x2. Why? Because there's no carry. So the whole of s is nothing but equal to this one here. And let's take a 2's complement of s. So 2's complement of s would be 2 to the power n minus this one here. So it is equal to x2 minus x1, which is nothing but the magnitude part here. Right? So this whole algorithm then makes sense of doing a subtraction of x1 minus x2 using the 2's complement approach here. All right, so let's illustrate that here. So let's say this is 1010 here. So what is this binary number here? 8 plus 2, 10 here. And what is the binary number here? So this is 4 plus 2, 6 here, right? So what we are doing is 10 minus 6 here. So let's take a 2's complement. So remember how we take the 2's complement? We keep the first 0 as it is, we keep the first 1 as it is, and then we flip the remaining. Right, so it becomes 10, 10 here. And so we add this up, right? So we add up the two numbers here. So 1010, 1010, we add up, and there is a carry here, right? So this is equal to the 4 bits here, 0100 here, and the carry is 1 here. So the sign is 0. Sign is 0, which means it's a positive number. And then this s is nothing but the magnitude part here, 0100, which is equal to 4 here. So 10 minus 6 is 4, and so it works fine. The whole procedure works fine and gives us the right answer here. Well, let's do the opposite here. Let's do 6 minus 10 here. So 6 here and 10 here. So let's do a 2's complement here. So 0, 1 will remain as it is. And then 1, 0 here. Let's add up the two numbers here. Note that there is no carry. Carry is 0. So carry is 0, sign is 1, which means it's a negative number here. So s is equal to 1100 here. And if you want the magnitude, take the 2's complement of this one. So 2's complement would be 001, and then flip this here. 1 here and flip it here, 0 here. So this is equal to 4 here, right? And it makes sense. 6 minus 10 is minus 4. Minus is indicated by the sign here, and magnitude is indicated by 4 here. And so what we are saying is the following. If you want to do subtraction, well, you can do subtraction if you represent the number x2 in 2's complement form. And you can use the same circuit for doing the subtraction here, for doing the subtraction. And what is the advantage of doing it? Well, the advantage is that doing a 2's complement is very simple. Because note that 2's complement is what? In fact, you can build a very simple circuit for building the 2's complement, and very simple circuit for building the 2's complement required here. So if we are looking at a complexity of circuit, so a simple circuit for doing 2's complement, a simple circuit for doing 2's complement here, and maybe an inverter here, have to be added to the adder to make a block which can do both addition and subtraction. It can do both of them, okay? And so instead of building a separate subtractor circuit, you can use the adder itself for doing both addition and subtraction, provided you represent the number in 2's complement and you follow this format here. Okay, so now what we are saying is that it's obvious that if you have numbers, binary numbers, you would like to represent them. The numbers may be positive and negative, and you need a representation for a number such that you can indicate the sign of the number also. So there are different ways of, so when you have a sign also, you need an extra bit to represent that particular sign here. So sign bit equal to 0 normally represents positive number, and sign bit equal to 1 represents a negative number here. So this is a representation which we call as signed magnitude. So the most significant bit is the sign bit here. So when the sign bit is 0, it means a positive number, and the remaining one is the magnitude part here. 0, 0, 0 is 0, 1, 1, 0 is 6, and 1, 1, 1 is 7 here. And then you have, the first bit, the most significant bit represents the sign, and the remaining 3 represent the magnitude here. So that's what we call as the signed magnitude representation. Name is obvious. First bit is sign. The next set of bits are the magnitude here. Then there is the signed ones complement here. So the first bit is sign. Note that sign here. First bit is sign. The next 3 bits here. So when you have -1, so you don't write it as the magnitude here. You don't write it as 001 the way you wrote it 001, but you write the complement part of it here. So the complement part of 001 would be 110 here. Ones complement here. So 110 here. So this is called signed ones complement. And then there is something called signed 2's complement here. So 0 to 7 is the same thing here. 0, exactly the same here. And then what you do is you build the 2's complement part. So when you take a 1 here, you build a 2's complement of 1. So first one stays as it is. And then first one stays as it is, and then you flip all of them, so you get 1, 1, 1 here. Right, so that's a 2's complement representation here. 2's complementation, so when you have -4, take a 2's complement of -4. So 0, 0, 1 will stay here, and then you flip this here, so it will become 1, 1, 0, 0 here. Right. So that's another way of representing a positive or a negative number. Positive number is as it is, except that you have added one more extra bit to represent the sign, which is 0 here. So 0 indicates that it's a positive number. MSB of 0 means positive number here. And then you take a 2's complement of 7, and that would indicate, note that the sign bit becomes 1, and that indicates a negative number here. So that's another way of representing, which is called as the signed 2's complement here. So if we represent numbers in 2's complement form, carrying out subtraction is same as addition here. Right? So, so positive number, note that if you have a positive number stays as it is. Right? So this whole part that we saw here, that we could do subtraction using an addition, well, if we use the 2's complement representation of a number, then so if, for example, if you're doing x1 minus x2, so you can take minus x2 as a negative number and represent it in a 2's complement form. So you don't need a separate block. What we are saying is that the x2 is available in the 2's complement form here. So x2 is a negative number and is available in 2's complement form here. x1 is a positive number available in 2's complement form here. And so if you work with 2's complement, then the adder circuit itself will work, will do addition, subtraction, whatever. Addition and subtraction are the same things here. The answer also you will get in 2's complement form here. Okay. So this is the 2's complement part here, right? So let's illustrate that. So it's basically what we are saying is basically note that the answer. So instead of showing it as separate, what we are saying is combining the two and saying that the whole answer is available in 2's complement form, and the numbers are also fed as in a 2's complement form here. And 2's complement form of x1 is nothing but the same number here, except that we are using one extra bit here. All right. So let's illustrate that here. So suppose you want to do +5 and +2 here. So note that to represent 5 and 2, you need actually 3 bits, but we've added another sign bit here. Right, so plus 5 and plus 2, so you know the answers that are there here. So both of them are represented in 2's complement form. So in a 2's complement form, a plus number is 0 and then 101, and so it's represented as a normal number here. Suppose you want to do 5 minus 2. So plus 5 you represent 0, 101, and minus 2 you represent as 2's complement of this one here, 2's complement here, right? So when you take a 2's complement of this, plus 2 here, 0, and 1 stays as it is, and then 1, 1. And then you add up. And when you add up, you get 0, 0, 1, 1 here. So that's the right number here, 3. So 5 minus 2 is 3 here. Minus 5 plus 2, well, you represent minus 5 in the 2's complement form that we just said. It is equal to 1011 plus 2 is 0010. You add up, you get 1101. So it indicates that when you get a 1 here, it indicates that it's a negative number here. And if you take a 2's complement form here, to get the magnitude, well, you get 3 here. So the answer is minus 3 here. But this is the answer in 2's complement form here. So the answer also you get in 2's complement form. The numbers are also fed in 2's complement form. And you can verify minus 5, minus 2. So each one of them is in the 2's complement form, and then you get minus 7 here. All right, so that's as far as the representation of numbers is concerned. So once you have a number and you can represent them, positive or negative, then the next thing that we need to do, so our interest is in doing computation. Our interest is in doing information processing using circuits. And so the next thing is, so obviously computation means you have to do algebra there, right? So you have to do algebra on binary numbers. So a variable x can take two values, 0 and 1. And so 0, you could interpret it in different ways. 0 could be, you could say 0 means false, 0 means no, 0 means in terms of circuit, low voltage, 1 means true, 1 means yes, 1 means in terms of circuits, high voltage here. So a variable x in binary system can take these values here, 0 and 1, right? And 0 and 1 may mean this, logically false, logically no, or in terms of circuit, low voltage and high voltage here. So basic operations that we do is something that you have already been exposed to. We can do an AND operation between two variables. So x1 dot is used to indicate x1 dot x2. So this AND operation basically means that y equal to 1 if and only if both x1 and x2 are 1. Otherwise it is 0 here. And we represent them in the form of what we call as a truth table. So truth table basically coming from that we are interpreting 0 as false and 1 as true. So a table which tells you when is y true, given the different values that x1 and x2 could take. x1 could be 0, 0. Then when x1 and x2 is 0, then is 0. When is 0, 1, again is 0. According to the definition of AND, when it is 1, 0, again is 0. Only when both x1 and x2 are 1, then only y is 1 here. So y is true only when x1 is true and x2 is true here. So a table like that is what we call as a truth table here. So the y depends on two variables here, x1 and x2. x1 can take any value 0 and 1. x2 can take any value 0 and 1. So together x1 and x2 can take 4 values, 0, 0, 0, 1, 1, 0, 1, 1. Right, so this is called the truth table, the relationship between y and the two variables x1 and x2 here. So that's AND. And there's an OR operation that we denote with a plus sign here. So y is 1 if either x1 or x2 is 1. Any one of them is 1, then y is 1. Or y equal to 0. To get a 0, you need to have both variables as 0 here. So its truth table is x1, x2, 0, 0 is 0, 0, 1. If any one of them is 1, y is 1, 1, 1, 1, 0, 1, 1, 1 is 1 here. Right, so that's called the OR operation here. So these are the algebraic operations, just like in a normal decimal system, you do addition, subtraction, and all of those things that you do. Here, these are elementary operations that we can perform, an AND operation and an OR operation, or an inversion operation. So y is complement of x here, not operation here. So if you have x is 0, y is 1. If y is 1, if x is 1, y is 0 here. So that's called complement of x here. Now, Boolean algebra has these postulates and theorems. And note that plus denotes an OR operation. So x plus 0 is x. So these are the postulates of Boolean algebra. So just like other systems, algebraic systems, you have postulates and you have theorems. So these are sort of self-evident statements. X plus 0 is x, x plus y, y plus x commutation here. X plus x complement is equal to 1 here. And x dot 1 is x, and all of these are here. Okay, so these are the postulates, and these are some basic theorems that you can use that will be helpful for manipulating binary numbers here. X plus x is x here, right? So x plus 1 is 1. If you take complement of x and you take complement again, that's equal to x here. X plus y plus z is here. This is what is an important theorem, De Morgan's theorem. X plus y whole bar is x bar dot. So the OR operation is converted into AND operation here. X plus xy is x here. So all these theorems that are there here, they can be proven starting from these postulates here. All these postulates can be used to prove any of these theorems here. So these are all useful results. We'll not get into, our interest is not so much in getting into the maths of Boolean algebra, proving things, but our interest is in seeing how we can make circuits which can exploit these properties and carry out computation in the binary number format. So for example, if you, just for the sake of completeness, say you want to prove x plus x is equal to x here, right? X plus x equal to x here. So x plus x can be written as x plus x dot 1. So we use postulate this one here, right? So these are with respect to the OR operation. These are with respect to AND operation. So we could use this one here, dot 1. So we're using this one here. 1, we could write it as, we use P4, x plus x bar here. And then we use P3 here, right? So x plus, so we use this one, this P3 here, x plus x dot x bar here. And x dot x bar is, we use P4 here as 0, and therefore we get x here. So we've proved that x plus x equal to x here. All right, so x plus x is not 2x, it's x plus x is, because these are logical operations here. X dot x is x here, so you can prove it using any of these. You can see the different steps that are there here. You can add a 0 here, or plus 0 here. 0 is x dot x bar here. Use P3 here. Use P3 here, this one, this P3 here. X plus x bar, use P4 here, x dot 1. And use P1 here, x dot 1 is x here, right? So x dot x is equal to x here, right? So these are useful results that we will see for calculating. Okay, so I will skip this. X plus 1 is 1 here, prove that. So you can see later on by yourself how x plus 1 is 1. And all of this, so let's, all of these things can be seen here through. De Morgan's theorem is interesting, which we use quite often. So it is when you have all these, a number of variables connected through OR, let's say, and you take a complement of this, so it becomes a complement of each variable, and then plus becomes a dot here. So OR operation becomes an AND operation here. Okay, and similarly then this kind of a thing, if you take a complement, so it becomes each variable gets complemented, and the dot AND operation becomes an OR operation here. So you can use this to simplify Boolean expressions here. So for example, what is x1 bar dot x2 plus x2 bar dot x3 whole bar here? So we use these results, right? Okay, so let's use that. So if you take a bar of this one, so it will become the complement of the whole thing, and the dot of this, and then the complement of x2, this whole thing. Yes, so the complement of this thing will become x1 plus x2 bar here, and complement of this thing will become x2 plus x3 bar here. Next we can multiply, we can take the product terms here. So x1 dot x2, x1 dot x3, x2 bar dot x2 bar, So that will be 0 here, x2 bar, x3 here. So that becomes our the simplified Boolean expression here. So this Boolean expression is equal to this Boolean expression here. So it's this De Morgan's theorem. These two theorems are used a lot, and plus those basic postulates and the elementary theorems that we talked about, they're all used to simplify Boolean expression. And so just like you know, in a normal algebra that we are familiar with, we have one variable, a function of another variable here. So for example, we are familiar that y is a function of x. Let's say it's a exponential function or a parabola here. So here also you have a function. You have y is a function of the y is a binary variable, and it's a function of two variables here, x1 and x2. Each one of them is one bit here, and y is also one bit here. And so the relationship here is denoted by an expression. Let's say here also we can denote it by an expression. But before that, just like we are using a graph to show a relationship between y and x here, the relationship between y and x1 and x2 could be shown in terms of the truth table here. So note that x1 can take 0 or 1, and x2 can also take 0 and 1. And therefore, together x1 and x2 can take values 0, 0, 0, 1, 1, 0. So you take x1, you put 0, and then x2 can take these two values here, 0 and 1 here. Then you make x1 equal to 1 here, and then x2 can take values 0 and 1 here. And then you write down what values y. So depending on the nature of the system, y, let's say 0, 1, 0, 1 here, right? So just like y is some function of x1 and x2. So y is 1 when x1 is 0 and x2 is equal to 1. And we can represent it in this form here. Y equal to x1 bar dot x2 here. So you can verify that only when x1 is 0. So note that y is 1 only when x1 is 0 and x2 is 1. Right? And here. So that's why there's an and operation, and x2 is 1 here. And x1 is 0. So we put x1 bar here. So when x1 is 0, so 0 bar becomes 1, and x2 is 1. So 1 dot 1 is nothing but 1. So y is 1 here. And for all other cases, you can verify that y will be 0 here. Okay. So that's a Boolean expression. So it's a Boolean expression which is describing this particular function, this functional relationship, which is in the form of a table is shown over here. All right, so let's look at this one here. So this is also a function. Y is a function of x1 and x2, and the relationship between y and x1 and x2 is shown by this truth table here. So truth table meaning if x1 is true and x2 is true, then y is false. So because of that notation, we call it a truth table here. So note that we can write this as y is 1 here. We can write it as x1 bar dot x2 bar here. So when x1 is 0, so 0 bar, 0 complement is nothing but 1, and 0 complement is 1, 1 dot 1 is 1. So that's true. So what would be the description of y in terms of Boolean expression in terms of y in terms of x1 and x2? So it's only 1 here. So y is 1 only when x1 is 1 and x2 is 0 here. So we write it as x1 1 and x2 0. So whatever is 0, we put a bar here so that 0 here it becomes 1, and 1 dot 1 will become 1 here. All right, so what happens if y is 1 not only when x1 and x2 are 0, 0, but also, note the word being used is also when x1 and x2 are 1, 1. So when it is 0, 0, well, it's represented by x1 bar dot x2 bar, right? When it is 1, 1, it's represented by x1 dot x2 here. So y is 1 not only when this is 1, but also when this is 1. So that's why we put an OR operation here. So if this is 1, then y is 1. If this is 1, then y is 1. If both of them are there, that also is fine. Okay. But both of them will not be 1 here, right? So when this particular term, when x1 dot x2 is 1, then this one will not be 1. All right. So given a truth table, we can write down a Boolean expression now. Right? So we look at when is y equal to 1. So it is 1 here. And we represent this by x1 bar x2, and then y is also 1 here, so we represent it by x1 and x2 bar here, right? So this becomes a Boolean expression. So instead of writing expressions as sum of terms that make y equal to 1, We can also write expressions. So note that this is a fully complementary. So here we are saying we are writing a Boolean expression by looking at when is y equal to 1. Well, you could also do by saying when is y equal to 0. So for example, if you focus on when is y equal to 1, so y is 1 here, so you would write it as x1 bar dot x2 bar. Y is 1 also here, so you'll write it x1 bar dot x2. Y is also 1 here, so you write it as x1 dot x2 bar. So y is sum of all three. So it looks like a complicated expression, right? But note that it's also true that you focus on 0 and you say when is y equal to 0? Well, it's 0 when x1 is 1 and x2 is 1 here. So we can write it in this form also. Y is x1 bar plus x2 bar here. So here we are focusing on when is y equal to 0. So note that when x1 is 0, x1 is 1, so x1 bar, this will be 0. And when x2 is also 1, so x2 is 1 and then the 0 here, and then it will give 0. For all other cases, note that y will not be equal to 0 here. Right, so this is an alternative way. Both of them are the same. Both of them, this expression represents the same truth table, same functional relationship, and this one also represents the same functional relationship. In fact, y equal to x1 bar plus x2 bar, so given an expression, you can generate a truth table by putting the different values. So you can put here 0, 0, and you'll find out what is y. You can put 0, 1, 1, 0, 1, 1, and you can find out y and generate a truth table. So you can go from a truth table to a Boolean expression. You can go from a Boolean expression to a truth table. You can represent the Boolean expression by looking at ones. You can represent the Boolean expression by looking at zeros. So for example, here is the only 0 term is here. So y is 0. So what you do is x1. So when it is 0 here, we keep it as it is. When 1 here, so we put a complement here. And instead of dot, we put a OR operation here. And you can verify that y will be 0 when x1 is 0 and x2 also has to be 1 then. Well, if you have, so this is also straightforward, so you can write it as x1 plus x2. All right, so when you have two zeros, well, y will be 0 when this is true and also when this is true. So you can write this one is x1 plus x2. This term is x1 bar plus x2 bar, and total y is written as x1 plus x2 dot x1 bar plus x2 bar. So note that y will be 0 when this term is 0 and this term is also 0 here. Okay. All right, so we can write it in this particular way. Any term is 0, y will become 0. If this term is 0, y will become equal to 0 here. All right, so any of these terms become 0, y will become 0. Okay, so obtaining Boolean expression from truth table, well, either you can focus on ones, right? So we could write this term here, note the first term, x1 bar, x2 bar, x3. That's the first term. And then the second term is x1 bar, x2, x3, like that. These are there. So you can focus on the ones and write down like this here. So we call this as the sum of product expression here, because each term is a product term and the overall expression is sum of these product terms here. We call it SOP, sum of product. Or you could write it in this particular form here. You could focus on zeros and you could write it like this here. So the first one is all zeros are there, so it's x1 plus x2 plus x3. The second one is 0 here, so it will be x1 plus x2 bar plus x3 here. This one would be x1 bar plus x2 plus x3 here. And this one would be x1 bar plus x2 bar plus x3 here, right? And each one of them would be, so these are all sum terms and then they're linked together through a product part here. So we call it product of sum form here. Okay, so there are two ways in which we can express Boolean expressions, in a sum of product form and in a product of sum form here. All right, so let's stop here. We'll continue with this discussion in the next lecture.